It is tempting to look at today's digital landscape and assume artificial intelligence is a sudden, modern invention. It feels like a product of the 21st century. But that assumption is entirely wrong. The theoretical architecture that makes modern machine learning possible is much older. The foundations were actually laid in the middle of the 20th century, long before the invention of the microchip. This chart maps the major milestones, tracing a continuous sequence of breakthroughs from 1943 all the way to 2015. But presenting this history as a straight, uninterrupted line of progress hides how this technology actually evolved. Progress was not steady. The true history of artificial intelligence is defined by violent cycles. It is a story of massive, speculative booms in funding and enthusiasm, followed inevitably by devastating institutional crashes. Researchers refer to these severe funding droughts as AI winters. They occurred whenever the extreme expectations generated by theoretical math collided with the hard physical limitations of early computing power. Mapping these cycles of booms and winters reveals how the industry was forced to adapt, pivot, and eventually rebuild the very systems we interact with today. The first cycle began in 1943, when researchers Warren McCulloch and Walter Pitts attempted to mathematically map the biological functions of the human brain. They proposed the first theoretical model of artificial neurons. By 1949, Donald Hebb expanded on this concept. He demonstrated a mathematical rule for modifying the connection strength between those artificial neurons, a process now known as Hebbian learning. The following year, English mathematician Alan Turing published a seminal paper titled Computing Machinery and Intelligence. In it, Turing proposed a framework to measure whether a machine could exhibit intelligent behavior that was indistinguishable from a human being, a concept that would become known as the Turing test. The field officially crystallized in 1956 at the Dartmouth Conference. There, American computer scientist John McCarthy coined the term artificial intelligence, formally establishing it as a distinct academic discipline. This period also saw the creation of early high-level programming languages like Fortran and Lisp. For the first time, researchers had the tools to translate complex logic into executable code. The results arrived quickly. Newell and Simon created a program called the Logic Theorist, which successfully proved 38 distinct mathematical theorems, often finding more elegant solutions than human mathematicians. This success triggered a period of extreme enthusiasm known as the Golden Years. Researchers developed highly visible projects, including Weizenbaum's ELIZA chatbot in 1966 and Japan's Wabot-1 in 1972, the first intelligent humanoid robot. Because these early programs could successfully simulate basic logic and conversation, researchers and investors assumed that broad human-level intelligence was only a few years away. That assumption set the entire field up for a massive collapse. Between 1974 and 1980, the enthusiasm evaporated. The industry entered the first AI winter. The ambitious algorithms designed in the 1960s had finally hit the physical constraints of 1970s hardware. The theoretical math was sound, but the computers of the era lacked the memory and processing speed to execute it. When practical commercial applications failed to materialize, government agencies and private investors aggressively pulled their funding. AI research ground to a near halt. To survive, the field had to abandon the dream of building a general, human-like intelligence. By 1980, the industry experienced a revival by pivoting to a much narrower approach. This boom was driven by expert systems. Instead of trying to build a brain, developers built programs designed to emulate the decision-making ability of a human specialist, strictly within a single, highly specific domain. Developers achieved this by interviewing human experts and manually programming massive, highly rigid sets of conditional if-then rules. This practical, corporate-focused strategy worked. It successfully restored institutional backing, a recovery marked by the first national conference of the American Association of Artificial Intelligence at Stanford in 1980. Narrowing the focus saved the industry's finances, but it resulted in incredibly brittle software. These systems could follow their programmed rules perfectly, but they could not learn, adapt, or process new information outside of their specific parameters. The limitations of that approach triggered the second AI winter, which lasted from 1987 to 1993. Rule-based setups like the XCon expert system ultimately collapsed under their own weight. As the lists of logical rules grew into the tens of thousands, the systems became computationally expensive and nearly impossible to maintain. Faced with high costs and inefficient results, governments and investors withdrew their capital once again. The exit from this second winter was not driven by a new theory. Instead, during the emergence era between 1993 and 2011, raw computing hardware finally became fast enough to execute the complex mathematics that had been theorized decades earlier. This alignment of hardware and theory was proved in 1997 when IBM's Deep Blue became the first computer to defeat world chess champion Garry Kasparov. Deep Blue was not thinking in a human sense. It simply possessed the immense processing capability required to brute force millions of potential chess moves faster than a grandmaster could evaluate them. By 2002, this processing efficiency allowed artificial intelligence to shrink down and enter the consumer home in the form of the Roomba, an autonomous vacuum cleaner mapping living room floors. By 2006, algorithmic processing had quietly integrated into the core operations of the business world, powering the recommendation and data systems for platforms like Facebook, Twitter, and Netflix. The emergence era stabilized the industry. It proved that artificial intelligence could be commercially viable at a massive scale by shifting the focus away from rigid rule following and toward rapid data processing. That focus on data accelerated into the current development model around 2011. This boom is driven by the convergence of deep learning and the massive global datasets known as big data. The methodology has completely inverted. Instead of engineers manually typing out endless flowcharts of rules, modern algorithms are fed vast quantities of raw data, allowing neural networks to autonomously map out statistical patterns. The power of this data-driven approach was demonstrated in 2011 when IBM's Watson won the quiz show Jeopardy! To accomplish this, Watson had to parse complex natural language and solve riddles, requiring a massive array of enterprise-scale servers. A year later, predictive algorithms reached the mainstream consumer market. In 2012, Google launched Google Now, an application capable of parsing user data to anticipate and provide information before the user explicitly requested it. In 2014, a chatbot named Eugene Goostman successfully convinced enough judges that it was a human being to win a high-profile Turing test competition. By 2015, ambient, voice-driven artificial intelligence became a standard household appliance with the release of the Amazon Echo, wrapping sophisticated natural language processing in an unassuming, consumer-friendly cylinder. The technology continued to scale. In 2018, IBM's Project Debater successfully formulated arguments against human master debaters, while Google unveiled Duplex, a virtual assistant capable of complex verbal interactions. Duplex was able to navigate a phone call to schedule a haircut appointment, responding to pauses and nuances so accurately that the receptionist on the other end never realized they were speaking to software. The theoretical frameworks proposed in the 1940s sat dormant for decades, limited by the computing power of their time. Today's systems represent those same concepts, finally executing at scale, powered by the massive datasets and processing speeds of the 21st century.